Hi there, this is Jacob Nash, Engineering Lessons, and in this video, I'll show you how to solve some stress-strain word problems. Now, there's a certain process that we can use that will make it a lot easier that PLTW provides, which is the 5-step process. Now, there's lots of variables in the equations that we'll be using to solve these problems. So this may not make sense unless you have looked at your own notes, only going by the videos I made in this unit where what problems we're solving may not make sense. But please look at some PLTW notes, which you should have access to if you're taking this course. So here are the variables we'll be using. First, we have a lowercase d. This is diameter. I'm not going to write it down, but you just hear what I say. Then we have r, which is radius. Then we have L, uppercase L, which represents length. Then we have uppercase A, which it represents area. Then we have uppercase F, which represents force. Then we have uppercase E, which represents modulus of elasticity, which was used in unit 3.1 on statics. Then here comes some Greek letters as usual. We have a lowercase epsilon that kind of looks like just a curly E, which represents strain. Then we have a lowercase sigma, which kind of just looks like a, I don't know what you could say that looks like. But it's kind of just like a O, lowercase o that just has like a dash on the top. Then we have a lowercase delta. So we've used uppercase delta, which looks like a triangle. But this time we're doing lowercase, which looks like basically just a curly D. At least to me, that's what it looks like. And that represents, sorry, I forgot to say, sigma represents stress, and delta represents deformation or elongation. These are all the different things that we'll have to solve for, and there's certain equations that we have to use. I can't write them all down at this moment, but you should have them on your PLTW formula sheet, which, once again, you should have access to if you're taking this course. So, let's just look at well, first, let's look at the process. What will we use to solve these problems? First, you need to write down what you know. In the problem, what it says, what do you know? Then you need to write what you don't know. What's the unknown? Then you need to draw the problem so that it will be easier for you to understand how it's working. Then you need to substitute and solve. And then finally, you get your answer with units. You need units. So there's units for each of those variables we talked about. Let me say what they are real quick. So back to what we have. You'll always need to convert to these units and write them in your final answer if needed. Diameter is in inches. Radius is also in inches. Length is also in inches. Area is in inches squared. Force is in pounds, lb. modulus of elasticity is in PSI. So also you'll sometimes see this as LB over inches squared, but they mean the same thing. Pounds per square inch, pounds per square inch, same thing. So, but I like to use PSI personally because it just seems easier to write. Then your strain is going to be in inches per inch. So you just say inch, inch. Then your stress is in PSI as well. And then your elongation has no units. The curly D looking thing, the lowercase delta, has no units. So you don't have to have units for that. So now that we have all these things in mind, let's go for some problems. Now I'm going to be doing a couple problems. I'll do 3 off of 2.3.1. And that way, I'm not going to do all of them. Like, in some units I've been able to do all, but just for video time's sake, I can't do that. But I will show you how to solve some of them so that you get the right idea. Let's first look at problem number 1. Okay, it says a weight of 18,000 pounds is supported on a rectangular base plate that is 9 inches wide and 2 feet long. The base plate rests on a concrete slab. Determine the stress that the base exerts on the concrete slab. Express your... we don't need that. Because we already know that stress is in PSI. That's all that was saying. Now, obviously, this isn't on the screen, but you should have this handy if you complete this activity. But if you don't have to complete this activity, basically, you're just going to want to underline each number you see, and then beside that number you underlined, say what it is. Write the variable beside it of what it represents. So the first number we see is 18,000, and a weight, that means it's a force. So a force of 18,000 pounds. Is force supposed to be in pounds? Yes. So we don't have to convert to anything. The next number we see is 9 inches and then 2 feet. So 9 inches wide, 2 feet long. Wide, that means that's the width, which isn't really a variable I showed you, but that's okay. We will just use that to find an area if needed. So that we said 9 inches. Is that supposed to be in inches? Yes. The length, though, it said it is 2 feet long. Is it supposed to be in feet? No. So we need to convert it to inches. To do that, sometimes in this course we've had to convert from inches to feet. When you do that, you divide by 12. But when you convert from feet to inches, you multiply by 12. So that's all we'll have to do. Multiply by 12 and we get 24 inches. There. What are the other numbers we see? No other numbers. And so we said our knowns. That was step 1. That's the things we know, but we don't know what stress is. So now we need to draw it. Let's draw what was in the word problem. So it said it was a rectangular base plate. So we can just draw a rectangle. And then we have a force coming down on it that's 18,000 pounds. Then we have a width of 9 inches, and then we have a length of 24 inches. So we drew it. There we go. That makes it simpler for us to understand what it's talking about. So how this relates to this unit, how much force can this thing take before it cracks? Now let's substitute. Well, actually, we need to think. I forgot to say, it's important to think of what equation you need to use. That's another step, really, before substituting. So we're trying to find stress. Looking at the equations that we have, we know that stress is force divided by area. So force divided by area. But we don't have area. That's not it. We don't have that. We only have width, length, and force. Well, force, we can use that in the equation, but we need to find area. And area, how can we find that? Well, there's also equations we can use, but the one that we need to use is length times width, because that has what numbers we already have found. So this is 2 steps we'll need to do. So first find the area, then we can find the stress, which is what we were asked. So we multiply 24 inches by 9 inches. And we get 216 inches squared, because that's the unit for area. There we go. Now we can plug in the things for finding stress. Force was 18,000 pounds divided by 216. And that turns out to be 83.33 approximately PSI. So our stress is 83.33 PSI. Simple, kind of. But that's how you would do it for that kind of problem. Let's look at a different kind. Some will be a little bit more complex. So let's look at an example of that. So that was number 1, but I'm not going to do all of them like I said. So, next, let's look at, let's see here. We can look at, sorry, I'm trying to think about it here. Number 8. This one's a difficult one. Now, I know I said I was going to do 3 problems, but unfortunately I can only do 2. If you heard a door open, apparently there's something that's come up that I have to do. So sorry about that, but I did one simpler one, now one more complex. Now, I'm not going to read the whole problem, but you should, and now let's look at all the numbers that there are. So, it said, the first number that we see is 240 feet long wires. So since there's 2, let's say L1, because, well, what this problem was asking is we need to compare the 2 materials that are stated in the problem and which one has the greater modulus elasticity. So we're trying to find modulus elasticity. So since there's 2 wires, for certain variables, we'll have to do a subscript of 1 and 2. So, but they're both 40 feet. The length are both 40 feet. But like I said, they have to be in inches. We multiply by 12 to get that. And when we multiply by 12, we get 480 inches. So that's what the length is for both of them. The length is equal. Now, the next number we see is there's a diameter of 3/8 inches, which, let's just put that into decimal form, which is 0.375 inches. And the diameter for the second wire is 0.1875. It's at 3/16, but it's the same thing. And then the next number we see is, we see that there's an elongation, or how much it stretches, which we represent with a lowercase delta that kind of looks like a D also, so don't get confused by that. So that's 0.1 inch, or wait, inch, yeah. Well, there's I said that there's not units for that, but there you can do inches in certain situations, and that would be the case. So now we need to find the modulus elasticity. So there. Now we can draw it. Let's draw what we have here. So I didn't read out the word problem, but if you did, you would know what this means. So let's do two wires. 1, 2. They both have a length of 480 inches. And then this one has a diameter of, I don't really have that much time to write it right now, but you definitely should. We will actually need to label these as W1, W2 for the wires. And then we have also the elongations. And there you go. And, oh yeah. I'm sorry, I missed that part. It also said that there's a force of 225 pounds. So let's put that there. And what equations will we need to use? Well, how can we find modulus of elasticity? Well, the equation we see is stress over strain, but we don't know either of those things, so that means we're going to have to definitely use lots more. So to find stress, we'll need to do force over area. So we're going to have to find a lot of things here. We don't know area, so to find area, we're going to have to use the equation pi d squared by 4. And then we also need to still find strain. And the equation for strain is, we have elongation over length. So, we have to use 4 equations. Gosh, this is probably the hardest problem. So, let me see here. First, we need to find the stress. But before we can find that, we need to find the area, actually. So, I'll have to erase all these things here, but you still should have it, just so I can have space to write it down. So, we see what equation we use to find area. And once you plug those things in, you get the area is, let me see, where is it? What did I get? Area for the, well, sorry, I apologize. You have to find 2 areas, the area for wire 1 and 2. So when you plug in the first diameter, you get that the area is 0.11 inches squared. And when you do the same thing for the second one, you get that the area is 0.03 inches squared. Now, we can find the stress. We have the force is going to be the same for both of them. So the stress for the first one is 225 divided by the area, which is 0.11. And when we do that, we get 2045.46 psi. Now, the second stress is 225 divided by 0.03, because that's up here. Now, when we do that, we get 7,500 psi. There we go. We found one part. This is our ultimate equation that we're trying to find things from. So luckily, we already found the top part. Now we just need to find the bottom part for both. Now, we use this. So the strain for the first one is going to be elongation over length. And we said that the elongation was 0.1 for the first wire, and the length for both of them was 480 inches. When we divide that, we get 9,818,208 psi. So that's the strain for the first one. For the second one, we use the same equation, and we'll divide. The elongation for that one was... Oh, I apologize. I accidentally just gave away the answer. I looked at the wrong thing. I knew that was confusing. I wondered why that was there. There is no there's no unit for the... I messed up earlier. There's no unit for the strain. There is a unit for the elongation, which is inches. Confusing myself. So, I looked at the wrong thing. Actually, 0.1 divided by 480 is 2.08 e to the negative fourth. That might look really weird to you, but don't worry, we'll fix. Really, that just means this. That's all that means. The e you can just think of as a times 10. When you do we had the elongation for the second wire was 0.25 divided by 480, because that's the length, and we get 5.21 e to the negative fourth. So now we have the bottom part of the equation as well. So for both of them, we need to divide the... Here's the answers that we got for wire 1. Wire 1, stress. Wire 1, strain. Wire 2, stress. Wire 2, strain. So we need to divide the two things. So for wire 1, we divide those two numbers. Now, you obviously probably can't type the e in the calculator. Just do times 10 for that. And when you get that, the random number I gave out earlier is the answer for the modulus of elasticity for wire 1 is this. Now for wire 2, we do the same thing. 7,500 divided by 5.21 e negative fourth. And then we get 14,400,000 psi. And there we go. And our question said which has the greater modulus of elasticity. Well, which number is bigger? This one. So that was for wire 2. Wire 2 has the greater modulus of elasticity. But which one is stiffer? That's going to be actually wire 1. Why? Because modulus elasticity means the higher it is, the more it can stretch. Meaning, the higher the modulus of elasticity, the less stiff it is. So, the lower modulus elasticity will be stiffer. That's why wire 1 is a stiffer one. So there you go. That was problems 1 and 8. And hopefully this video helped. Sorry that it was a little bit rushed, because that's what I had to do. But I hope this makes sense. And if you have any questions, feel free to comment below. And that will actually be the last video of this unit, even though it's the second one. And next, I'll do unit 2.3. So see you then.